All right, let's jump into another deep dive. Today, we're taking on something we experience every single second, like literally constantly. Gravity.
Ooh, yeah.
You sent over some super interesting stuff from the Gravity of the Situation, the podcast about, well, universal gravitation.
Yeah.
And I gotta say, I think we're in for a pretty wild ride.
Yeah, I think so too.
We're gonna unpack how we even began to understand gravity, going way back, and then boom, all the way to Einstein and his like totally mind-blowing theories.
It really is fascinating,
Yeah,
how something that feels so familiar can still be such a deep mystery.
it
I mean,
is.
we all know, like, gravity keeps us on the ground,
Totally.
but it's also, like, the thing that makes planets orbit stars, galaxies spin. It's everywhere.
It's the glue, right? And we just like take it for granted, but imagine like no gravity, poof, the universe as we know it gone.
Right. Just wouldn't exist.
So let's start like super basic. What IS gravity?
Yeah.
It's got to be more than just like stuff falls down, right?
Oh, definitely. Way more. For ages, people saw things fall and, well, they came up with some pretty out there explanations.
Like what?
Like the ancient Greeks, Aristotle, they believed that everything had its own special place in the universe.
Yeah.
Heavy stuff, like rocks. They wanted to be near the center of the earth,
Oh, okay.
while light stuff, like fire, tried to reach the heavens.
So like everything was just trying to get to where it belonged.
Exactly.
Huh. Well, I guess that makes sense, kind of, from their point of view.
Right.
But then Galileo came along and was like, nope, not buying it. He was all about the experiments, the observations, the real deal.
Totally, yeah. Galileo's experiments with ramps and stuff showed that everything accelerates at the same rate because of gravity.
Wait, really?
Yeah, it doesn't matter how heavy or light something is.
But hold on, a feather falls way slower than like a bowling ball.
Right, but that's because of air resistance.
Oh, right.
Yeah. If you took away all the air, like in a vacuum, they'd fall together, side by side.
That's kind of mind-blowing. You'd think the bowling ball would just like plummet.
It's not always what we expect, is it?
Definitely not. It makes you think, like, how often does our intuition totally miss the mark, especially when it comes to physics?
All the time.
So speaking of physics, we can't talk about gravity without mentioning the OG, Isaac Newton, and that whole apple thing.
Ah, yes, the apple.
True.
Probably more of a story than real life, but it gets the point across.
Right. So what's the point?
Well, Newton realized that whatever made that apple fall was the same force that kept the moon hanging around Earth.
Huh.
Gravity wasn't just an Earth thing, it was like a universal thing.
Universal is right. His
Yeah.
law of universal gravitation is like, whoa, dude, when you really stop and think about it.
I know, right?
It's saying everything in the universe attracts everything else.
Everything.
That's insane.
Right, and it all comes down to how massive things are and how far apart they are.
Okay, break it down for me.
So the bigger something is, the stronger its pull. And the further away things are, the weaker the gravity between them gets.
So, like, if I move twice as far away from something,
The gravity's 4 times weaker.
whoa,
Yeah.
that's wild. So from teeny tiny dust particles to giant galaxies, they're all tugging on each other constantly.
A never-ending cosmic dance. All thanks to gravity.
It's beautiful, but also kind of terrifying when you really think about it.
It is.
And it works so well to explain, like, most of what we see happening around us, right? But then Einstein comes along and drops this, like, theoretical bomb.
General relativity.
Right. He basically said gravity isn't just a force, it's like a warp in the fabric of space-time itself.
Yeah, totally different way of thinking about it.
So how does that work?
Okay, imagine like a bowling ball on a trampoline.
Mm-hmm.
It makes a dip, right?
Mm-hmm.
That's kind of what massive objects do to space-time. They warp it. And other things moving through this warped space-time, they follow those curves, and that's what we feel as gravity.
Wait, so the Earth isn't actually pulling on the moon? It's just like following the curve made by Earth.
Yeah.
That's so trippy. And Einstein even said that light, which doesn't even have mass, would bend around massive objects because of this warping.
Exactly.
And they actually saw that happen during a solar eclipse, right?
Yeah, they did.
Which, like, proved him right.
Pretty amazing.
Totally revolutionized our understanding of gravity. And speaking of real-world stuff, I read that GPS, like the thing on our phones,
Oh, yeah.
it relies on Einstein's theories to work right.
Absolutely. Those GPS satellites are way up there, experiencing weaker gravity than us down here.
Huh.
Makes their clocks run a tiny bit faster. If we didn't factor in that relativity stuff, GPS would be useless. You'd be miles off course.
Whoa, so something that seems super abstract, like relativity,
Yeah.
actually affects our everyday lives.
Big time.
Okay, so we went from like apples falling down to space-time being warped.
Hmm.
It's a lot to process, and I guess this is where things get even weirder, because this warping can lead to some seriously bizarre stuff, like black holes. Black holes are like gravity gone wild,
You
right?
could say that, yeah. Places in space-time where gravity is so strong that nothing, not even light, can escape,
It's like the ultimate cosmic vacuum cleaner.
pretty much.
Okay, so I've heard about this terrifying thing called spaghettification.
Oh, yeah.
Is that as bad as it sounds?
So let's just say you wouldn't want to experience it. As you get closer to a black hole, the gravity difference between your head and your feet becomes extreme.
Okay.
You'd be stretched out like, literally, like spaghetti.
Oh, God, no, thank you. I'm good. But luckily, the nearest black hole is, like, super far away, right?
Yep, very far. And actually, you know what? We have one in our own galaxy.
Wait, what?
Yeah, right in the middle of the Milky Way, a supermassive black hole.
And we even have a picture of it, right?
We do. In 2019, the Event Horizon Telescope captured the first ever image of a black hole's shadow.
It's like staring into the abyss.
I know, right? A selfie with a cosmic monster.
That's amazing and kind of terrifying all at the same time. And wait, didn't scientists actually hear black holes colliding?
Yeah, through gravitational waves. These are like ripples in space-time caused by supermassive events, like when black holes smash together.
So Einstein predicted these like 100 years ago.
Over a century ago, yeah.
And then in 2015, boom, we finally detected them.
Crazy.
So it's like the universe itself is ringing when these massive things collide.
Okay, exactly.
That is so cool. But it also shows us like how much we still don't know about gravity.
Oh, definitely. We've come so far from just watching things fall to understanding how gravity warps space-time and creates these crazy, powerful events.
Right.
But there's still so much to learn. Like, what about dark matter and dark energy? These are some of the biggest mysteries in cosmology today.
Okay, I'm hooked. Tell me more about that. Like, what are they and why are they such a big deal?
Okay, so dark matter first. Astronomers notice that galaxies spin way faster than they should, based on the stuff we can actually see. It's like there's this invisible stuff adding extra gravity to keep them together.
So we call that dark matter.
Exactly. And from what we can tell, it makes up most of the matter in the universe.
Whoa. So most of the universe is made of stuff we can't even see.
Mind-blowing, right?
Totally.
And then there's dark energy, which is even more mysterious. In the late 90s, we found out that the universe's expansion isn't just continuing, it's actually speeding up.
Wait, seriously?
Yeah. Something is pushing everything apart, working against gravity.
And that's what we call dark energy.
Yep. But we have no idea what it actually is.
So most of the universe is made of stuff we can't see, and there's this invisible force pushing everything apart. This is like a cosmic mystery novel, and we're only on part 1.
It is. Right.
So much more to explore.
Welcome back to our gravity deep dive. Last time, things got pretty intense, right? We went from ancient theories to Einstein's warped space-time and even explored black holes. And oh yeah, those mysteries of dark matter and dark energy. Seriously, it makes you realize gravity is so much more than just, like, keeping us on the ground.
It really does.
It's like woven into the very fabric of the universe,
Yeah.
shaping everything from teeny tiny particles to those massive cosmic structures.
It's the architect, right. So speaking of keeping us grounded, let's like bring gravity back to Earth, literally.
Right.
How does gravity affect us like in our daily lives in ways we might not even realize?
But think about something as basic as walking.
Yeah.
Every step relies on gravity.
Well,
It keeps us balanced, in control. Without it, we'd be like flailing around like those astronauts trying to walk on the moon.
I've seen those videos, hilarious.
Right.
But seriously, it makes you appreciate how gravity is like always working behind the scenes, even when we're just doing normal stuff.
Absolutely.
So it's not just about like moving around.
No, not at all. Gravity affects how our muscles and bones develop,
Mm.
our organs function, even how fluids are distributed in our bodies.
Mm-mm.
It's a lot.
So gravity is like the silent partner,
Right.
always shaping our physical existence.
I like that analogy.
Yeah.
It's true. It's a force we rarely think about consciously, but its impact is profound.
Totally. And it goes beyond our bodies too, right? We talked
Mhm.
about GPS, but I bet gravity plays a role in tons of other technologies we use all the time.
You're right. Think about it. Those GPS satellites wouldn't stay in orbit without the pull of Earth's gravity.
Oh, right.
And it's not just that. Gravity's crucial for things like hydroelectric power, predicting the tides, even making sure airplanes fly. It's like the unsung hero of the modern world.
I never thought of it that way. So every time I check my phone for directions, every time I hop on a plane, I gotta thank gravity.
Pretty much.
Okay, let's shift gears for a sec, talk about something a bit more dramatic.
Okay.
Volcanoes. How does gravity play a role in those fiery spectacles?
Ah, volcanoes. They're a great example of how gravity interacts with other forces to like shape our planet.
Okay.
So you know how molten rock, magma, is less dense than the surrounding rocks?
Yeah, density, like how tightly packed the matter is.
Exactly. So that less dense magma, it rises up because of buoyancy, but gravity is pulling it down at the same time.
So like a tug of war,
Yeah, and all that creates this immense pressure under the Earth's crust.
like a giant pressure cooker.
Right, and gravity's like holding the lid on tight. But eventually, that pressure needs to escape somehow.
Boom, eruption.
Exactly. And even then, gravity's still in charge, shaping how the lava and ash flow down the volcano.
So it's like this fiery dance choreographed by gravity.
It's a great way to put it.
It's amazing this force that keeps our feet on the ground is also behind these incredible displays of power.
I know.
And I bet it's involved in other large-scale things too, right? Like
Yeah.
shaping the whole planet.
Absolutely. Mountains, valleys, continents, they all owe their existence to gravity. It's like this constant sculptor working over millions of years, from those towering mountain ranges to the vast ocean basins. It's all thanks to gravity.
We've covered so much ground today. Walking, volcanoes, shaping continents. It all comes back to gravity.
It's pretty humbling, isn't it?
It is. But looking ahead, what are some of the big questions scientists are still grappling with when it comes to gravity?
That's a great question. One of the biggest challenges is trying to merge Einstein's theory of general relativity with quantum mechanics.
Ah, yeah, you mentioned that before. It's like trying to fit two different puzzle pieces together, but they just like don't quite match.
That's a good way to put it. Relativity, which explains gravity as curved space-time, works amazingly well for big stuff. Planets, stars, galaxies.
Right.
But when you zoom in to the subatomic level, where quantum mechanics rules,
Yeah.
the two theories just don't seem to get along.
So scientists are trying to find a way to bridge that gap, the universe of the super large and the super small.
Exactly. And it's closely tied to gravity, because we need a theory that can handle how gravity behaves at both ends of the spectrum. Some physicists think the answer might lie in something called quantum gravity. It would be this, like, unified framework that brings those two worlds together.
That would be huge, wouldn't it?
That's
It'd totally change our understanding of how the universe works. And what about those mysterious forces we discussed earlier?
Dark matter and dark energy.
Yeah. Are we any closer to figuring those out?
It's a hot area of research. Scientists are building incredible detectors, buried deep underground, hoping to catch a glimpse of dark matter particles.
Really?
Yeah. And others are studying the way galaxies are spread out in the universe, searching for clues about dark energy. It's an exciting time for cosmology.
So much we still don't know about gravity. From its role in the quantum world to those invisible forces shaping the cosmos, it's all a bit mind-boggling.
I know, right?
But I guess that's part of what makes it so fascinating, right?
Absolutely. The more we learn about gravity, the more we realize how much more there is to discover.
Welcome back for the grand finale of our gravity deep dive. We've journeyed from those ancient theories to Einstein's warped space-time, even explored the power of black holes, pondered dark matter, and dark energy.
It's amazing how gravity, this force we feel every single day, can lead to these like mind-boggling possibilities.
Right.
It's where our current understanding of physics really gets pushed to the edge and our imagination can really take off.
Okay, let's start with wormholes. I've seen them in movies, you know?
Yeah.
Like shortcuts through space, you jump in and bam, you're across the universe in the blink of an eye. But is that even remotely possible in real life?
Well, wormholes are theoretical tunnels, right?
Okay.
And they could connect really, really distant points in space-time. Imagine like folding a piece of paper in half and then poking a hole through.
Hey, visualizing it.
That's kind of like a wormhole.
Yeah.
It creates a shortcut so you don't have to travel the whole surface of the paper.
So theoretically, you could jump into a wormhole here and pop out on the other side of the galaxy without actually traveling all that distance.
Theoretically, yeah.
That's insane. But you're saying theoretically for a reason, right? What are the catches?
Well, there are a few, and they're pretty big ones. For starters, wormholes are thought to be incredibly unstable.
Oh.
They might collapse faster than you can even blink.
So it's like trying to drive through a tunnel that's constantly caving in. Not exactly a safe road trip.
Not at all. Plus, we have absolutely no clue how to create them or control them.
Right.
Some theories say you'd need this exotic matter, something with negative energy density, which we've never actually observed in the universe.
So even if we found a wormhole, we might not even be able to use it.
Yeah, probably not.
That's a bit of a bummer. But hey, at least the idea's out there, right?
Hmm.
So what about time travel then? Is that even remotely possible according to physics?
Time travel is another concept often linked to gravity, especially within Einstein's theory of relativity. See, one of the things relativity tells us is that time isn't this absolute fixed thing.
Okay.
It's relative. It could be affected by things like gravity or how fast you're moving.
So does that mean if I travel super fast or hang out near a black hole, I could actually travel through time?
Some theories say that extreme gravitational fields, like those around a black hole, could warp time enough to create something called a closed time-like curve.
A closed time-like curve.
It'd be like a loop in space-time, allowing you to travel back to the past.
Okay, so a time loop.
Yeah.
That sounds amazing and also potentially disastrous.
Right.
Like, what if you went back in time and accidentally prevented your own birth?
Exactly. Those paradoxes are one of the biggest challenges to the whole idea of time travel. They suggest there might be some built-in limitations, even if we could manipulate space-time like that.
So time travel is still more of a, like, captivating idea than a real possibility, for now at least.
Pretty much.
But before my brain melts from all this time-bending talk, let's move on to something equally mind-blowing. Extra dimensions.
Okay.
Is it actually true that our universe could be just one slice of a much bigger, multidimensional reality?
The idea of extra dimensions is a big part of several theoretical physics ideas, especially string theory.
String theory, right.
Yeah.
Everything's made of these tiny vibrating strings.
That's it. And string theory suggests that those tiny strings, the most fundamental building blocks of everything, they need more than just the 3 dimensions we see to vibrate in. In some versions, there might be as many as 10 or even 11 dimensions.
Whoa. So our 3D world is like a flat sheet within this much larger multidimensional space?
That's a really good way to think about it. We can't directly observe these extra dimensions, but string theory proposes they're curled up, incredibly small, totally hidden from us.
So they're all around us, but we're just not equipped to see them.
It's a wild idea, isn't it?
Totally.
Cool.
Does the existence of these extra dimensions actually affect gravity in any way?
That's one of the big questions, yeah.
Okay.
Some models suggest that gravity might be able to leak into those extra dimensions, which could explain why it seems weaker than the other fundamental forces in physics.
So we might not even understand gravity fully because we're only experiencing a fraction of its power.
It's a possibility.
It really makes you think, doesn't it? Like, how much are we missing just because of our limited perspective?
Definitely.
This whole deep dive has been an incredible journey. We've covered so much, from dropping apples to warping space-time, and even explored those mind-bending ideas in theoretical physics. I feel like my brain has expanded a few dimensions itself.
It's been so fun exploring these ideas with you.
And who knows what amazing discoveries are waiting for us, right?
Mhm.
Maybe one day some of these crazy concepts will be part of how we understand the universe, just like everyday knowledge.
We can't wait to see what the future holds.
Me too. It's been an amazing ride. Thanks for joining us on this deep dive into the world of gravity. It's a force that shapes our universe, our planet, even our bodies, in ways we're only beginning to understand. So keep looking up, stay curious, and never stop exploring the mysteries of the cosmos. Until next time.